Hello all, I am Santa Kumar from Computer Science and Engineering Department. Our project is a lightweight REST-based multi-access edge computing framework for 6G networks. In the 6th generation, networks are expected to support ultra-low latency, high reliability, and massive connectivity for next-generation applications such as XR, autonomous vehicles, smart manufacturing, and real-time healthcare systems. Despite these advancements in multi-access edge computing, the current deployments always rely on heavyweight orchestrations and the frameworks such as Kubernetes or NFP Nano, which introduce significant control plane overhead and resource consumption. To address these limitations, we are introducing a proposal model which is called a lightweight REST-based MEC framework that eliminates dependency on full-scale orchestration platforms like heavyweight orchestrations and enables direct efficient service management at the edge of the networks. We are using REST-driven service registration, deployment, invocation, and monitoring. The proposed framework reduces control plane complexity and heavyweight orchestrations. The statement of the problems is to reduce heavyweight orchestration dependencies and resource inefficiency at the edge, and then non-deterministic service instantiation, and then lack of transparent performance visibilities. The focus areas: to develop and design a lightweight REST-based MEC framework for the future 6G networks. We are implementing REST APIs for edge service lifecycle management, and then reduction of control plane overhead by removing heavyweight orchestration layers, and then integration of edge level monitoring for latency, response time, and resource usage. And the target audience: 6G edge computing scenarios requiring ultra low latency and high reliability, and then resource constrained edge nodes such as micro data centers and single node deployments. We are delivering a REST-based MEC framework prototype which supports edge-level service lifecycle management. And then inclusions, like we are including REST-based framework for the MEC networks, and then edge-level service registration, deployments, and invocations. And also we are including service lifecycle using REST APIs, and then we are reducing the control plane overhead without using heavyweight orchestration tools. And then simple and efficient edge service execution model was also included. And what are the things we have excluded are: there are no Kubernetes, there are no hardware accelerated edge processing, and then there were no cross-domain or multi-operator orchestrations. And then also no end-user application layer implementations. The edge services and the REST-based modules are classified based on the REST service descriptors, and we are also building a automated service lifecycle and invocation logic in our projects. Edge service datasets like request, response, and performance logs. The limitations are: the performance depends on edge node resource availability, and the system latency varies with the network's load and request volume. Based upon the network loads, it will varies and to high to low, and different edge platforms follow varied deployment configurations. The REST-based operations may introduce network communication overhead. And requirement analysis includes identifying the 6G edge computing requirements like latency, constraints, and resource limitations. The framework we follow is REST-based service workflows. REST-based MEC framework implements REST APIs for service lifecycle management at the edge, which defines request handling, routing logic, and the response management. And then edge service deployments deploys lightweight services on edge nodes using containerized on-process based executions. Testing, the process is tested under various performance and various request loads and edge conditions, and we can validate the results by comparing it with the traditional MVC orchestration and with the lightweight REST-based MVC orchestrations. Workflow includes defining the edge service parameters, setting service access and invocation rules, assigning service endpoints and roles, deployment, lightweight REST service logics, and then monitoring, updating, and managing the service status. This is the architecture diagram which follows the lightweight REST-based mechanisms. And these are the various UML diagrams for building our projects. The algorithm lightweight REST-based which act as a core execution engine of the MEC framework which manages service registration, deployment, startup, shutdown and terminates through REST APIs. For example, low latency request, direct REST invocation, immediate service response. Resource constraint modes, lightweight runtime control, minimal CPU and memory usage. Concurrent workloads, simple load routing with request level performance and monitoring. The nodes are selected like the map registered services to available edge nodes based on the availability of the CPU memory capacity and then based on the runtime also. The request routing and invocation modules assigns routing paths for service execution. High priority means local edge execution for ultra low latency services. General priority distributed routing with simple load handling. Hardware and software selections. To run these projects, a minimum of dual core or higher processors is required and minimum 4 GB RAM is required and 120 GB hard disk of storage is required. Implementation. As we know, the system is implemented using a modular REST-based architecture. We are following a REST-based frameworks for developing these frameworks. Okay. These are the important code segments for our projects which we developed using a fast API. These are the various test cases we have tested by requesting high loads to low loads and many services at the edge based on the REST APIs, and we as expected we got the results. And in result, the system successfully automated student workflow by generating like the proposed frameworks deliver lightweight REST-based edge computing architecture that enables low latency services, deployment, and efficient resource utilization for emerging 6G networks. From this, in the future 6G networks, we can follow the REST-based MEC network which is lightweight, which delivers the services at low level without relying on high orchestration layers. The modular microservices and decentralized edge support dynamic application placement, improving scalability, flexibility, and responsiveness across heterogeneous networks environments. Overall, the system provides a future-ready MEC solution that supports next-generation 6G application through lightweight design, REST interoperability, and distributed edge intelligence. Thank you.